the laminar flow in a circular tube. So this is the one. If I show you the derivation, I need couple of lectures. So I don't want to do that. I just only show you the solution of after a lot of calculation or solution we may get, and I can give you some overall idea. So if you want to see exactly how it comes, you have to do it using the book. Book has step by step some formulation they already showed, but I don't want to show you here. So what is there? We, based on the, I already showed you the differential element, we can take the temperature one. We have a T here on the right side, T plus this one using the Taylor series expansion. And then from here to there, we have like a heat flux or the heat transfer from bottom to the top. So if we consider this differential element, then from the thermal energy equation, okay, conservation of energy, or from here we can get this equation. Okay, and then for fully developed region, not earlier than that, when it's fully developed region, we can get, if we solve this equation, when you do this equation, where you can do some integration, then at the end we can get this equation, because we have to do 2 times integration, and then we can get this equation, okay, which has 2 constant. So we have to get the value of the constant, and these 2, C1 and C2, it easily we can get it applying the boundary condition. Okay, so if R is equal to 0, what is the boundary condition? If R is equal to the R naught, I mean on the surface, what is the boundary condition? So if we apply just, I need only 2 boundary condition to get this C1 and C2. So we are getting, applying that, we are getting C1, C2, and this is the solution of temperature in respect to R and X. Okay, the radius and the distance. So in these 2 parameters, we have this. Now, if we can remember, I told you in my last lecture, the velocity, fully developed velocity profile. So it is actually the parabolic profile. I told you last time, if you can remember, that if R is equal to R naught, it is 2. If R is equal to 0, it is 2. So we can, if R is equal to 0, if R is equal to 0, it is 2. If R equal to R naught, it is 0. Okay, so this is 0 and this is actually 2 if R equal to R naught. What does it mean? It means here, this is our actually 0. Okay, so velocity profile looks like this. So if R is equal to 0, and this is R is equal to R naught, and this is R is equal to minus R naught. Okay, so and this is R is equal to 0. So when it is 0, you can see the maximum velocity. And if R is equal to R naught, velocity is 0. If R is equal to minus 1, if you can put it here, minus 1, minus R naught, it is 1. So 1 minus 1 is equal to 0. So that means the velocity is 0. So these 2 surfaces, velocity is 0, and in the middle, the maximum velocity. And it looks like a parabola. Okay, so if we apply, if we put this value in that equation, in this equation, because we have this velocity term here, you can put this on here, then it looks like this. Okay, and then these 2, sorry, this one and that one, sorry. So this equation here, this equation and that equation, if we put this on this Tm, the average temperature I showed in my 3rd slide, if you put here, then ultimately at the end we can get the mean temperature this. So 1148, it is a nice number. We need this number sometime. Okay, so this is the average temperature. So okay, we are writing it again, the mean temperature here again. Now come to the point here. So we know that from the equation I showed you here, just go back to, in this, here we have, in this equation actually, here, if we put this, it is actually dtx. So it is d tm, we can call it ts minus tm by, actually we are coming here, ts minus tm is equal to, we have this, this is our rho. We also have this on this side, and we have a dx at the end. So this dx we have, yes, qx is our h, and then what else? You have h and ts minus tm. So this is the ts minus tm. That ts minus tm we are taking here. Okay, then only we have h here, and then we have m dot cp. So this kind of thing. So after rearranging all of this, we are actually getting this equation. We are taking the dx just below that one. Okay, so when you are getting this one, then we can do the integration, and then we obtain this tmx minus surface temperature x is equal to minus 11/48 qs double prime, that is the heat flux, d by k. So d is the diameter and k is the thermal conductivity. Now you see very strange. Here you can easily get h is equal to 48 divided by 11 k by d. Okay, so this is our h. We can get the h from here. So how to get the h? I can show you here that Tm minus Tx equal to minus 11 by 48 Qs double prime D divided by K. Okay, so yeah, that's the, I hate it. Minus 11 by 48, and Qs is equal to Q double this is equal to your H. You will have H, and then you have the Ts minus Tm. So that means Tm minus Ts, then we can make it plus. So that means Tm minus Ts. Okay, and then we have D by K. So now we have Tm minus Ts on the left, and now this one cancel with 1 here. So now if we take H is equal to, so K will go up and D will come down, and then the 48 will be reversed. So that means 11 by 48 will be 48 divided by 11. So actually this. So you see, it's a very concise way. I just showed the results. But if you are interested, you can see this, how it comes. Okay. So our H, the heat transfer coefficient, is coming to 48 by 11 K by D. Now, from the Nusselt number definition, we have H D by K. So H D by K. That is our Nusselt number. Okay. So now we know H. What is H? 48 by 11. And K by D. And here we have D by K. So this cancel. So now we have a very constant Nusselt number, which is 48 by 11, which is 4.36 for heat flux condition. So this value will be needed. Okay, so you will need this value. You okay? You understand this one? How you get this value? Because sometimes student ask question, how did you get it? How did you get this 4.36 Nusselt number? Actually, Nusselt number came 4.36 from this way. So this is fully developed region. But if it is not fully developed, then how to do that? How to calculate it? So there are some correlation again, but that is 434.36 plus something. So that is coming here. So that is for fully development, this one, and circular tube, uniform surface temperature. So for uniform surface temperature, we have Nusselt number is 3.66. And we have 4.36 for uniform, I mean the constant heat flux. So now come to the point. If we have some thermal entry length problem, so when it comes to the thermal entry length problem, then we have the correlation, this one. You see, 3.66 for temperature condition. If it is like a temperature condition, it's not like a heat flux condition, temperature condition, then this 3.66 plus we have some this correction things. Okay, so this GZD, that's called Gates number, which is D by X RE PR. So Reynolds number times Prandtl number times the diameter divided by where is the length, where you are calculating. Okay, so if you know where you are calculating, you put the value X in there. Okay, and then if you get this correlation, you can easily calculate the Nusselt number, the average Nusselt number. But it has a condition. The condition is it can only use if it is a constant thermal condition, not constant heat flux condition. If it is a constant thermal condition, you can use this correlation. And if your Prandtl number is greater than or equal to 5, only you can use this correlation. So yesterday, one of my students actually contacted me and asked me that he's confused about a lot of correlation, which one I should use. Yes, it is true. I also confuse sometimes. But the thing is, if you do practice, you'll be able to understand. Because I'm not telling that you have to read whole books. I'm not giving you that things to do. What I'm telling is what I'm doing in my lecture. That follow this lecture and similar problem. So that means you can see this kind of correlation. You don't need to use any other correlation. There are lots of correlation in the book, but I'm not interested in all those. These are the correlation I'm using in my lecture and in the tutorials. That is actually important for our daily life. But there are a lot of other correlations. People, when they did the research, they got those correlations. I think that correlation is maybe some other sophisticated problem if you want to deal in future. That is different things. That time you can learn by yourself. But for this subject, we will restrict ourselves to use couple of correlation, not the whole set of correlation. Okay. So if you follow my lecture, if you follow the tutorial, so you know which correlation you will use. Okay, you will not be confused. But if you don't attend my lecture and if you don't listen to my video, I asked the student, did you watch my video? He said no. Do you attend my lecture? He said no. So you see, so if you don't watch my video, watch my lecture, or you don't attend my lecture, you will be confused. That's for sure. But here I'm telling you all the steps, what is the relationship, what time, under what condition you should use which correlation. Okay. So now this is one case. So if your Prandtl number is greater than or equal to 0.01, you can use this one. So see, for this correlation and that correlation, it's almost you see, it looks very complex. Okay. But the difference is here, this researcher who developed this correlation, the guys Case and Hussain, so they developed this one for Prandtl number greater than or equal to 5. Okay. But this one they developed, these two guys, they did another Karishma, and then they developed for Prandtl number 0.012. What does it mean? This is more robust. So you can use this one When your Prandtl number is between, not between actually, from 0.1 to 5, you can use this. And when your Prandtl number is greater than 5, you can still use this one. Okay? So now it is up to you. If your Prandtl number is water, 7, which one you want to use? You can use either this or